So we've been working through equilibrium problems dealing with solubility. And so we're up to sample problem 19.9, but I just want to do a little review of some of the problems we've done before and just have you see that really we've done all these problems before. We're just applying them to a new system. So for example, here was problem 19.5. This was the first problem that we dealt with in our solubility section. It was, all right, write an equilibrium constant, which for slightly soluble compounds we call it KSP, standing for solubility product. So we had to learn how to draw or write equations for slightly soluble compounds and then think about their KSPs. The next problem was kind of what we call a type 1 equilibrium problem. So that was saying, you know what? When we know the solubilities, that gives us equilibrium concentrations of species. If we know equilibrium concentrations of species, we can put them into an equilibrium expression to solve for the equilibrium constant. So we worked on kind of what we called a type 1 problem. The next one was working on what we kind of called a type 2 problem, which is, you know what? We know an equilibrium constant, so let's use that to figure out equilibrium concentrations. And so this one was a pretty straightforward problem with calcium hydroxide to figure out what is the 2-to-1 ratio of hydroxide to calcium that we'll have when we put a chunk of calcium hydroxide in solution and allow it to break apart. A little bit of a variation on this was looking at common ions in solution with our next problem. And so the idea was if we had that same chunk of calcium hydroxide that we put in a solution, if there was already calcium that was there, how will that affect our ability to dissociate the calcium hydroxide that was in a solid form? Well, the common ion effect, and if we think about this from Le Chatelier's principle, if we push on this equilibrium on the product side, we shift the equilibrium to the left, which makes this product less soluble. So common ion effects will always decrease the solubility of a salt. So what we move on to now is thinking about the effect of solubility when we've added a strong acid. And what we'll see as we work through these is it's really kind of another one of the Le Chatelier's type principles, where what we're going to do potentially when we add a strong acid is we're going to have chemistry available with one of the products. And when we have chemistry available with one of the products, we can pull it out of solution. Pulling a product out of solution is going to shift an equilibrium to the right. If we're talking about a solubility equilibrium, shifting it to the right means we've made the salt more soluble. So just kind of a little bit of a preview there to kind of set up what this problem is going to do. So like we just saw with our earlier sample problems, if you've got to go back to chapter 4 to review how to draw chemical formulas given a name, you've got to make sure that you're very comfortable with that. Lead-2 bromide. Okay, we need to think about what happens with lead-2 bromide. So lead-2 bromide is this. Dissociates to lead ions and bromide ions. And if we think about, if we've got H plus in solution, remember when we talked about, our buffers and our titrations, we use these sheets, right? And the first question we need to ask ourselves, who's in solution? So when we think about who's in solution, well, we've got H plus, we've got lead 2 plus, and we've got Br minus. We're not going to have two things that are positively charged interacting with one another. So there's no chemistry there. So the question is do we have any chemistry that happens with H plus, which is again an acid, and Br minus, which is a conjugate base? So what we really need to do is we need to ask ourselves, let's look at HBr. If HBr is a weak acid, that means H plus and Br minus are going to want to rejoin and make HBr. Well, we know that HBr is a strong acid. So being a strong acid, it wants to exist apart as bromide and H plus ions. So if that's the case, there's no chemistry that's going to happen between these. So in this problem, there's no effect with the addition of H3O plus from a strong acid on the solubility of lead bromide. All right, let's apply that same thought process to copper hydroxide. Copper 2 hydroxide. So copper 2 hydroxide looks like this. Breaks apart. Oops, I keep wanting to write calcium there. Breaks apart to copper ions and hydroxide ions. Maybe you already can see where this is going. But if we've got H plus in solution, again, no chemistry is going to happen between two cations, but we have the potential, right, to have chemistry happen here. Does H plus like to react with OH minus? Absolutely. That was the chemistry that we saw with a strong acid, strong base titration. They want to react with one another and make H2O. If they react with one another and make H2O, that means we are removing a product. If we remove a product, the equilibrium shifts right. If the equilibrium is going to shift to the right, that increases the solubility. Last one, iron 2 sulfide. So it's iron 2 plus, sulfide is S2 minus. So this guy as a solid will break apart into lead ions and sulfide ions. And so asking the question again, H plus, not interested in doing anything with iron 2 plus. But if you want to think about chemistry that's available here, sulfide is the conjugate base of a fairly weak acid, which means it wants to be HS. If you remember back a little bit when we're doing and writing our KSPs, do you remember this one from sample problem 19.5? We're never even going to really see S2 minus in solution. This is such a strong conjugate base that if it finds water, it's going to actually generate HS minus and OH. So just by having H3O plus in solution, that's even going to favor that reaction even more. So in this case, we're going to have HS form when we have a strong acid in solution. Same as we had above, we're going to be removing a product. So our equilibrium shifts again to the right. That will increase solubility. So a way to think about how Dr. Parenti could permute this problem, for example, for quiz or exam questions, we don't have to think about adding a strong acid. I could just ask about changing the pH. So I could ask the same question by saying decrease the pH. Or we could talk about increasing the pH. In that case, increasing the pH with this problem would actually act like a common ion effect and shift the equilibrium back to the left, and that would decrease the solubility of the copper hydroxide. So as you're working through problems, kind of a great skill to practice is thinking about how you could see this problem in a different way, because that's generally how I make most of my exam questions.